Good evening to all of you. In this video, we wish to see how to write the normal constraint equation. The normal constraint equation is also called as the wedge constraint. Let us try to understand what this is. Supposing we have a horizontal surface and there are two blocks M1 and M2, and let us say we apply a force here. If we apply the force here, what we expect is both these bodies will stick together and move with a common velocity. That is what we expect. Yes, and that's what will happen also. Now, when we say these two bodies are moving together with a common velocity, let us try to understand what we mean by that. This surface of M1, if I call that as surface 1, if it moves by a distance x1, if it has a displacement x1, and this surface 2 of M2, we will call that as surface 2, if it has a displacement of x2, we are saying if the two bodies are in contact, they remain in contact all the time, then the displacement x1 must be equal to the displacement x2. Why do we say this? If x2 is greater than x1, m2 would be ahead of m1 and there would be no contact. But we are putting the condition that yes, there is contact between these two. Similarly, if x1 is greater than x2, we have a case where m1 has crashed into m2 and the surface has entered into m2. That crashing situation also we are not considering. So therefore, when the two contacts are have not been disturbed or the contact is there, we say x1 equal to x2 or v1 equal to v2 if you differentiate it. You take the derivative, you get v1 equal to v2. If you again differentiate it, you will get a1 equal to a2. Now if you see, the normal force between m1 and m2 will be acting along this line. Yes, this is the direction of the common normal. This is the direction of the common normal. If you see, these velocities and accelerations are along the common normal. So when we put this condition a1 equal to a2 or v1 equal to v2, we are basically saying the velocities along the common normal of the two surfaces must be the same, or the accelerations of the two surfaces along the common normal must be the same. Now, this body m1 can even have a vertical velocity like that. If I call that as vy, it can have a vertical velocity like that while maintaining the contact. So there is no restriction or constraint on the motion of m1 vertically, but there is a constraint or restriction on the velocity of m1 and m2 along the direction of the normal. So that is why we call it as the normal constraint. Okay? Let us take an example where we have a wall and a floor. This is a wall and this is the floor. I am showing a body like this of this shape, okay, resting against the wall, and you have another body over it of this shape. Let us call this as M1 and this as M2. Yes, we wish to find out the accelerations of these two blocks. It's a block on block, and also the values of the contact surfaces at every contact. So let us see how these bodies will move by drawing the free body diagram. If I draw the free body diagram for M1, yes, I shall show M1 as a particle on this line. Let us say this angle is some theta. Let us say this angle is some theta. So on this line, I shall show M1G, that is the weight. Now there will be a contact force between these two surfaces in contact. It will be normal to the surface. So N is going to be like this. Remember, N is a pushing force. So this surface pushes the other surface by this surface pushes the other surface by a force N. That is the normal force. Now the wall will also exert a force. If this block is now getting pushed against the wall, so therefore the wall will exert a force N wall. This would be the forces. If you see, because this block is pushed towards the wall and making contact with the wall, it can have only a downward acceleration. So this body will accelerate downward. Here. Yes. Let us draw the free body diagram of M2. For M2, similarly I will show this line. This is making an angle theta. So this is theta. I will show M2G. There will be an equal and opposite N on this by Newton's third law. And then there is going to be a force from the floor. There is going to be a force from the floor. I will call it as N floor. Now we may expect a force from the wall as well, but if you see the free body diagram, N has got a horizontal component. That horizontal component will move this bottom block to the right, so it will lose contact with the wall. So therefore, there is no normal force by the wall on this block. Now, let us write the equations. Before we write the equations, we can say that this block will move to the right with an acceleration a2, and let us see after a certain time how the whole system looks. Yes, this block would have moved to the right and the other block would have come down like that. Yes, that is how the system is going to be after some time. Now let's write the force equations. So let us resolve this. If I extend this vertical and this normal line, this angle would be theta, this is going to be theta. So along the vertical you have m1g downward and n cos theta, that is also in the vertical direction. So for this we can write m1g minus n cos theta is equal to m1 into a1. That would be the first equation. Then, since the block is not moving, the upper block is not moving in the horizontal direction, the net force in the horizontal direction must be 0. So the horizontal component of n is n sine theta. So we can say n sine theta will be n by the wall. That is the second equation. Coming here, this angle would be theta. So we can now resolve n. Now this is accelerating, having an acceleration towards the right. So that will be provided this acceleration will be due to the horizontal component of n, which is nothing but n sine theta. Yes, you resolve n cos theta and n sine theta. So n sine theta will be equal to m2 into a2. That is the third equation. And in the vertical direction, this block does not move vertically. The bottom block does not move vertically. It moves only horizontally. So the vertical forces must nullify. So we have n cos theta plus m2g equal to n floor. So n cos theta plus m2g is equal to n of the floor. This is the fourth equation. Now you see the number of unknowns. You have n by the wall, n by the floor, a1 and a2. Whereas we have, so there are 5 unknowns and we have only 4 equations. The fifth equation will be the normal constraint equation. Let us see how we get that. I will show the common surface here like this. This is making an angle theta with the horizontal. Let us show both the accelerations. A1 is this way and A2 is this way. Yes? And what is the direction of the common normal? The common normal, the normal force is along perpendicular to the surface. This is 90. Yes, let me. Yes, that is the direction of the common normal. Direction of normal. I would say common, okay. Direction of the common normal. Normal force by 1 on 2 and 2 on 1 will be along this direction. So this angle will be theta, corresponding angle. This will also be theta. So now we apply the normal constraint. The acceleration along the direction of the common normal must be the same. So this would be, if you complete this rectangle with A1 as a diagonal, the component along the common normal here would be A1 cos theta. Similarly, if you complete this rectangle, the component of A2 along the common normal would be A2 sin theta, the opposite side. So A1 cos theta must be equal to A2 sin theta, or basically we have A1 is equal to A2 tan theta. That will be the fifth equation. So there are 5 unknowns and 5 equations. We can easily solve for them. Yes. Let's take up another example. We have a fixed incline now on which there is a block. The block is not cuboidal. Let us see how it is. We have the incline here. This is fixed. It's a fixed incline. And on this, there is a block of this shape. Yes. And on this block is another block which is being guided by, there is a guide here like that. It is being guided. This is a fixed guide. All surfaces are frictionless. We are not showing friction anywhere. And the system is released from rest. We can call this mass as M1 and this as M2. So this block M2 will come down, and as this comes down, the horizontal surface of M2 will also come down, and this block M1 will come vertically down. So M2 will have an acceleration A2 this way, and this block within that guide, yeah, this is the guide, frictionless guide, and this block will come down this block will come down with an acceleration a1. Yes, we need to find out the normal forces and the accelerations. So let us draw the free body diagram. For M1, it will be M1G, and there will be a normal force, vertical normal force, and like that. For this block on the incline, we will show the incline like that, and the block as a particle M2G. N, there will be an N like that downward by the upper block on the lower block, that is N, and there is going to be an N by the incline like that. Yes, so those are the three forces: N by the incline, N by the top block, and M2G. So let us now write the equations. This is A1, so we can write M1G minus N is equal to M1A1, first equation. For this is accelerating downward. Yes, this is accelerating. So I will write this as N2G plus N, both downward. This is accelerating downward at A2. This angle is theta. So if I extend this is going to be theta. So along the incline, the force is going to be M2G plus N sine theta. So we can say M2G plus N sine theta. That force will accelerate M2, is M2A2. That is the second equation. And the components perpendicular to the incline, that will nullify, because this lower block has motion only along the incline, not perpendicular to the incline. So therefore we can say N of the incline, N incline will be equal to M2G plus N cos theta. That is the third equation. If you see the number of unknowns, you have N of the floor, you have A1 and A2, whereas we have only three equations. The fourth equation would be the constraint equation, normal constraint equation. The contact surfaces are horizontal. So this is going to be the direction of the common normal. Direction of the common. Now A1, we will show A1 along this, because A1 is vertically downward, and this is A2. This is A2. Yes. So the component of A1 along the direction of common normal is A1 itself, because A1 is along the common normal. The component of A2, this angle is theta, so this is theta. So the component of A2 would be A2 sine theta. So by the normal constraint, we can say that these two accelerations must be equal. So A2 sine theta equal to A1. That will be the fourth equation. So therefore, using these four equations, we can find out each of these four values: N, L floor, A1 and A2. Let's take up another example. Here we have a wedge and a block on a wedge. So I'll show a wedge here like that. Wedge is a movable incline, So this is theta and there is a block here. The mass of this is m1, mass of this is m2. So again you would like to find the accelerations and the normal forces. This is on a, everything, all surfaces are smooth. So here what you are going to find is that this block will of course slide down the incline, but the incline of the wedge, and the wedge will move towards the left because the normal force by the block on the wedge will have a horizontal component which points towards the left. So the wedge will move towards the left. Now if we call this acceleration as a dash with respect to the wedge, and a2 is the acceleration of the wedge, then the absolute acceleration of m1 is the vector sum of these two. Yes, if you are on the wedge and viewing this block will have an acceleration a dash. The wedge is moving towards the left. So therefore, the absolute acceleration a1 of m1 would be, if I show a dash like that and a2 like that, this will be the direction of a1. So a1 will be the vector sum. a1 is the vector sum of a dash plus a2. Yes. Now we can do one thing. We can resolve, this angle is theta. We can resolve a1 along the incline and perpendicular to the incline. Let me draw a perpendicular here and complete this rectangle. So this is, we will call this as ay, and this we will call it as ax. Yes, ay and ax. Ay plus ax is a1. So a1, magnitude of a1 would simply be root of ax squared plus ay squared. Okay. Now let us see the normal constraint. The two surfaces are in contact on the along the incline. So let me show the contact surface. The contact surface is like this. This is the direction of the common normal. This is the direction of the common normal. So along this, if you see, you have the component of a1 along the common normal is ay. This is ay. Ay is along the direction of the common normal. Now the component of a2 will be a2 sine theta. So a2 sine theta would be in this direction. Ay would be equal to a2 sine theta. Yes, by the normal constraint equation. This equation is also called as the wedge constraint since we are applying it to a wedge and a block. That's the alternate name. Both are synonymous. So this is one equation, the wedge equation or the normal constraint equation that we have here. Now let's write the other equations. Let us draw the free body diagram for M1. For M1 you will have M1G downward, there will be N upward. These are the two forces, and for 2, block 2, you would have M2G, there would be an N like that. Yes, this is the incline, and there is going to be the normal force from the floor. So there would be a normal force from the floor for the incline. So this angle is theta. This is theta. So this angle is also theta. So we can now write the equations here. Let me So this angle, this is theta. So this angle is theta. So I can write an equation along AX and along AY. Along AX, we will have m1g sine theta. m1g, if I complete the rectangle here, this is opposite side. So m1g sine theta will be equal to m1 into ax, because ax is along the incline. Perpendicular to the incline, you will have m1g cos theta here. You will have m1g cos theta minus n is equal to m1 into ay. So that makes the equation 2 and equation 3. For this, for the wedge, it is n sine theta which is going to provide the necessary horizontal force. Yes, if I complete the rectangle here, the opposite side is horizontal. So n sine theta will be equal to m2 into a2. That is the fourth equation. And along the vertical, n cos theta plus m2g will be n from the floor. That is the fifth equation. So what are the unknowns? The unknowns are n by the floor, ax, ay and a2. So you have 5 equations and 5 unknowns. Once you know ax and ay, a1 can be found out as root of ax squared plus ay squared. Let us take up another example, this time involving a string. Supposing we have an incline, a mobile incline of angle theta, and let us say it has got a pulley here, and here you have the wall, there's a string connected to this pulley, and there is a block, we'll call this M1 and this is M2. Okay? And we would now like to find the accelerations of M1 and M2. Now, note one thing. Let us say M2 moves to the right by x2, by a distance x2. This string will reduce by x2 and it will get released here as x2 on the incline. Yes? But this x2 is on the incline. That is, it is with respect to the incline. It is not from the ground frame. So x2 would be x dash. x2 would be x dash. The motion of the block on the wedge. That is, if you are positioned here and watching, you are positioned on the wedge. If you are positioned here on the wedge and watching, you would find this coming down by x dash. So therefore, if this is acceleration a2 and the acceleration downward is a dash, we can say a2 and a dash will have the same magnitude. Yes? So therefore, now we can show the accelerations. Let us say this is a2 and this is a1, a dash. This is a dash. Now vectorially, we saw, as we saw in the previous case, a1 would be a dash plus A2. So this would be A1. This is A dash and this is A2. Yeah. So again, we can do the same thing. We can resolve A1. This angle is theta. This angle is theta. We can resolve A1 as AX and AY. This is AY. And resolve AX and AY. Let me draw it for you again. This is A2. This is A1, A dash. This is A dash. This is A2. This we are resolving as AX and this as AY. This angle is theta. This angle is theta. So we will apply the normal constraint. This is the direction of the common normal. This is the direction of the common normal. So along the common normal we will have AY for the first body and for the uh, second body you will have A2 sine theta. A2 sine theta. So basically you have these two would be equal. So you have AY is equal to A2 sine theta. That is the normal constraint equation. What about AX? AX we can say is A dash. AX is A dash plus the component of A2 along AX. That is A2 cos theta. Now it is a vectorial sum. AX is equal to A dash plus the component of A2 along the x direction. Yes. So AX would be A dash plus A2 cos theta, but vectorially A2 cos theta is opposite to AX, so we put it as A2 cos theta. And A dash we know is A2. So this would be A2 minus A2 cos theta. That gives AX as A2 into 1 minus cos theta. That is the other equation. So we have the equation for AY, we have the equation for AX. Next, what you need to do is write the force equations for each of these. For the force equations, if you draw the free body diagram for the block there will be tension upwards, there will be M1G downward and N like that. That would be the free body diagram for 1, M1G, N and T. So we can find the components along the x direction, along the y direction, along the x direction, along the y direction. Let's find that. Okay. Mg, M1G, this is N, this is T. Yes. So this angle is theta, this is theta, and we have this as ay and this as ax. Yes, ax. So you will have, if you resolve this now, you will have m1g sine theta will be along the incline, m1g sine theta minus t will be equal to m1 into ax in the along the incline. Then along the normal, along the perpendicular, this will be m1g cos theta. So this is the third equation. Along the perpendicular, you will have m1g cos theta minus n is equal to m1 into ay. That will be the fourth equation. Then let us now draw the free body diagram of M2. For M2, you will have at this point, if I show the pulley as a point, there will be a T like this and a T like this, and there is going to be MG, M2G, there would be an N like this, yes, there would be an N like that. This angle is going to be theta, and there would be a normal force from the floor. Yeah. Okay. So now for the horizontal forces, this angle is theta. This would also be theta. So you will have n sine theta. N sine theta is the horizontal force plus t. T is also in the same direction as n sine theta minus t cos theta. Minus t cos theta would be equal to m2 into a2. That would be the fifth equation.